Hi everyone, my name is Anastasia Flynn. I'm a psychoarchitect for Arc Systems in Atlanta. In this presentation, I will show you how I've been using server-side JavaScript Unreal in production projects over the past year to make my life as a developer easier. This presentation is not about JSS. I have nothing against JSS. It will be public as of Sitecore 9.1, and I'm thrilled to finally start using it. But server-side JavaScript is not just for JSS projects. Everything I will demo, you can start using it in your existing MVC projects. The agenda is to demonstrate real applications of server-side JavaScript at these 3 steps of a Sitecore project lifecycle. I want to show you, backend devs, what JavaScript can do for you and why you should care about it. I will introduce you to a handful of the most popular Node frameworks, and we will even make our own Node module. For setup, we will automate the generation of new Sitecore solutions with Yeoman. For development, we will build a modular TypeScript library against a headless CMS with Webpack. For testing, we will enforce Helix design principles with unit tests written in Jasmine and run with Karma. We're going to jump right into creating our own Node module. So, assuming you already have Node installed on your machine, which is just a matter of Googling install Node and running an executable, the next step is to create a folder on your machine where you want your Node module to live. So here, I'm creating a folder called module demo. And I'm going to run a terminal window, and I'm going to use the command npm init. This command will guide me through some questions which are used to initialize my Node module. The only value that's required at this point is the module name, and for everything else, you can just hit enter to use the default values. You can see that the initializer creates a file called package.json. This file is very important. We will see it a lot in today's demo. This file declares metadata about your module like title, description, and version. It declares third-party dependencies and their versions, and it declares commands that your module exposes. So what can this Node module do for us at the setup phase of a Sitecore project lifecycle? This phase is when time is spent on gathering requirements and setting up development environments. As we all know, development environments for Sitecore projects are quite complex. There are multiple integration points to manage, and it's important to develop a setup process that's consistent and repeatable. My company spins up multiple new Sitecore projects every year, and even though each project has unique requirements, there are certain foundational elements that need to be repeated every time. There are C# projects to set up, which includes setting up Helix structure, proper Sitecore NuGet references, and build profiles. There's TDS projects, which includes validation rules, package generation, glass model generation. There's code style configuration, TypeScript and Sass compilation, bundling and minification. This is a very long list. And it's very time-consuming and error-prone to build this out manually every time. That's where Yeoman comes in. Yeoman is a project generator that lets us automate our unique Sitecore solution spin-up processes. We can create a template for new projects that's source-controlled and collectively managed. As teams try out cool new tools or error handling techniques or something else in their projects, they can roll this back into the template so everyone benefits from the learnings. Yeoman is a generic scaffolding system. Yeoman by itself doesn't make any decisions. Every decision is made by generators. In other words, you build the cookie cutter and provide the dough. Yeoman is just the oven. Other developers will be able to use your generator even if they're not familiar with the inner workings of Yeoman or the node stack that powers it. In the next slide, I will start building onto the Node module that we initialized a few minutes ago and turn it into a Sitecore project generator. The prerequisite is having an existing Sitecore project that you think is a good candidate to become your standard cookie cutter. Looking at the package.json file from the Node module we created, I need to make a couple of small tweaks to prepare this to become a Yeoman generator. The module name needs to start with generator dash, and the keywords need to contain the phrase Yeoman generator in order to show up in searches on Yeoman's site. These changes can be made directly in the package.json file, as I have done here. I also removed some properties that were auto-generated by npm init that aren't relevant to the generator. The next step is to add dependencies. I prefer using Yarn rather than npm to manage my dependencies. So my first step here is to install Yarn, which I do with the npm install yarn with the global flag command. This will install Yarn globally on my machine. The next module I will install is obviously Yeoman, because we can't do anything without that. Next, I'm using the command yarn add UUID to install a module that I will use to generate GUIDs. And finally, I'm using the command yarn add gulp rename, which I will use to dynamically rename files. You can see that as these modules are being installed, our package.json file is being updated with the module names and their versions. Once the dependencies are downloaded, the next step is to decide how to break up your model solution into logical pieces, because you probably don't want one giant generator for everything. You want a base generator for the stuff that will definitely be used by every project, and then you want sub-generators for the stuff that's less commonly used. In my demo, I'm grouping the Helixified, C# and TDS components into the main generator, and I'm separating out the TypeScript and Bootstrap parts of the application into sub-generators. This is a great strategy to follow because it means that all projects that use my generator won't have an automatic dependency on TypeScript and Bootstrap. Once you have the main generator and sub-generator organization figured out, create a folder in your node module root called generators. And add a property called files to package.json that references the name of this new folder. This files property is how Yeoman knows where to look for generators. Inside the generators folder, create folders for your main generator and each of your sub-generators. Within those, you need a file called index.js and a folder called templates. Index.js is the JavaScript file that's executed when you run a specific generator. We'll take a closer look at this file in a minute. The templates folder is where Yeoman looks for template files for specific generators. What do I mean by template files? Template files are the files that will be used to create your new project. This is where the custom part of Custom Project Generator comes in. These template folders need to be filled with a base structure that's unique to your company, based on whatever existing project you're using as your model project. Now, obviously, any existing project is going to have project-specific values scattered throughout, and these need to be replaced with variables. When Yeoman runs a generator, it doesn't just copy and paste these template files to the destination. It's a lot smarter. It creates a virtual copy of your templates and exposes them as a stream to you to manipulate and transform. Only once the transformations are done does it write the final versions of the templates to disk. So, for variables that can be manipulated at generation time, Yeoman respects EJS syntax. EJS is a simple templating language. Here's an example of what it actually looks like when you replace your project-specific values with EJS variables. This is the TDS scproj file that we're looking at. It looks a little complex, but all the work lies in identifying the complete list of project-specific values that need to be replaced with variables. Once you have the list, it's just a matter of using a find and replace tool to do the grunt work. Here's a good starting point of what to look for when you're making your own list. Now that we have our templates, let's circle back to that index.js file. This is the entry point file that gets run when someone runs your generator. The requirement for this file is that it needs to define a class that inherits from Yeoman's generator class. Once we have the class, we need to create functions that represent the various steps that our generator needs to do. Yeoman follows a convention-driven approach for function names. This means that functions that have special names will be prioritized in accordance with this diagram. So, for example, if you have a function named initializing and a function named prompting, initializing will run before prompting. If you have any functions that don't follow these conventions, they will run during the default step. You can also have private helper functions. Just name them starting with an underscore like this, and Yeoman will ignore them. In the next slide, we will deep dive into how I've implemented index.js for a real Sitecore project generator, which I will demo shortly. Going top to bottom, the initializing step logs a message and creates a settings object. This settings object will be used to store input entered by the dev who's running the generator. The prompting step uses Yeoman's prompt function to prompt the developer for project-specific variable values. Yeoman handles all the work of making prompting work. We just need to tell it the list of variables, the text to show to the developer, and whether each variable is required or has a default value. My prompting step is broken up into two sub-steps. In this first one, I ask for the Sitecore version and I present the dev with a list of options. In this second one, I ask for the .NET Framework version, and I limit the list of options based on the selection that was made for the Sitecore version question. By chaining your prompting questions like this, you can make your prompter intelligent and help developers avoid errors. The configuring step saves all the variable values that have been provided to a config file on disk. This makes them available for reuse by sub-generators that may be run at a future time. The writing step is the main guts of the generator. This is where templates are copied and transformed. First, any files that don't have a file name, only an extension, like gitignore and editor config, need to be copied with the source path and destination path explicitly provided. Otherwise, Yeoman will ignore these files. Then all the normal files get copied. For these, the source path and destination path do not have to be specified. Yeoman will use the templates folder as the source path, and it will use the place where the generator is being run as the destination path. This is when the transformations happen. Here, I transform certain file names based on the namespace variables supplied by the developer. All the other variable values, as well as some freshly generated GUIDs, get fed into Yeoman's fs.copyTemplate function, which will process transforms inside file bodies per EJS syntax. Now, you may be wondering why my prompting and writing functions are calling out to an external file. The reason is that I have factored out some of my operations into external helper classes so that they can be reused again by sub-generators. After all template files are copied over, the install step calls yarn install to resolve all node dependencies in the newly created project, and the end step outputs a log message. Let's see this in action. This is the same node module that we created earlier, and I have populated it with Yeoman templates and index.js files like the ones I just showed you. Now I will run npm link. npm link is a way to publish your node module locally. It creates a virtual symlink to your node module so that you can use it as though it was a real module downloaded from npm. Now that the generator is exposed locally, I can put myself in the shoes of a developer who's running the generator to scaffold a new Sitecore project. I've created a new folder called Demo Test, where I want my new Sitecore project to live. So let's go ahead and run this. The way to run a generator is with the command yo and then the generator name. So in my case, that's yo Sitecore Flynn. This is going to launch into those steps that we just saw. So it's going to log a message and then go into our prompting step. So it's asking me for all those variable values like solution name and MVC area name. If you recall, I had that one step where I asked for Sitecore version and then I presented the dev with a bunch of options. So we'll see what that looks like. Here it is. So once all the prompting is done, and let me pause it so we can see it, this is where the writing step happens. And here it's copying over all the templates. It's doing all the transforms and renames. And once the writing is done, we can see on the bottom it called yarn install. So now it's going to install all the node dependencies in the new project. If you look in the top left, we can see that a whole bunch of files were added to our new folder. So there's our end message. So let's see what this generator created. So this is that yo.rc JSON file. This is what saves the variable values that I supplied during the prompting step. So future subgenerators can use these settings, and I, as a developer who ran this generator, won't have to provide them again. I can look inside the node modules folder to verify that my node modules were actually installed successfully, and they were. Let's go into source here. We can see that everything was renamed per the namespace variable that I provided, so that looks good. I'm going to open up this Visual Studio project that was generated. So what we have here is C# and TDS projects in Helix structure. I'm going to open up Task Run Explorer and make sure that all my gulp tasks are loading okay. They are, that's good. I'm going to open up the TDS output and make sure all those projects look okay. So everything looks great. So from here, I'm all set. I can start writing code or working on CI/CD. Let's look at a scenario where the dev wants to run one of the optional subgenerators. I'll use Add Bootstrap as an example. The process is very similar for subgenerators, though they usually have less code since they don't need to prompt for as many variables or write as many templates. In the case of Add Bootstrap, the initializing step logs a message and reads the config file that we previously saved to disk. The writing step uses Yeoman's fs.extend JSON function to add a list of new node dependencies to the existing package.json file. These dependencies are third-party libraries needed to use Bootstrap. The writing step also copies over a starter pack of base Sass and HTML files that a front-end dev can use to work on a website's Bootstrap code. Finally, the install step calls yarn install to download the new node dependencies based on the changes made to packages.json. So this is where we left off in Visual Studio. And just a couple of things to note here. Right now we have 5 gulp tasks. And if I open up package.json, we'll see that we have no production dependencies right now, only dev dependencies. So I'm going to go back to my terminal and run the subgenerator. So the way to run a subgenerator is yo generator name : subgenerator name. So in my case, that's yo Sitecore Flynn : add bootstrap. This subgenerator didn't have any prompting steps, so it's going to go right into copying over the template files. But since it is modifying my package.json, it does ask me to confirm that overwrite. So I hit yes for that. So the subgenerator is complete, so let's see what it did. When we go back to Visual Studio, it detects that package.json has changed, and we can see that our production dependencies have been modified. We now have Bootstrap, jQuery, and Popper.js, which are all Bootstrap dependencies. If I refresh my gulp tasks, we can see that a whole bunch of gulp tasks were added relating to Bootstrap. And since my node modules have already been updated, I can go ahead and start working with these gulp tasks. I don't need to do any additional steps. So I can run vendor copy to copy the Bootstrap JavaScript files from the node folder into my local project. Then I can run assets compile to compile my Sass into CSS. And then finally, I can run assets serve, which is a gulp task that launches a local server that lets me test my CSS. So if I was a front-end dev working with Bootstrap, I would be ready to go. So by using a Yeoman generator, we collapsed the work of setting up a working Cycler solution with all these project pieces down to under a minute. With that, let's jump to the development phase of the Cycler project lifecycle. Helix is a pattern for managing dependencies, and it allows for modular components that are reusable and testable. When devs think about implementing Helix, we usually think about it in terms of how to structure our C# projects and our Cycler items. And JavaScript is often overlooked. But if we're building renderings with a rich UI, then our projects end up housing large JavaScript libraries. And to get the most out of these JavaScript components, to reuse them, unit test them, dependency inject them, they should adhere to Helix principles as well. To allow Helix in our JavaScript libraries, we need a dependency resolution and module bundling tool. In today's demo, we will look at Webpack. There are other bundlers out there like Rollup with simpler configuration if all you want is the bundling part. I'll be using Webpack because it not only does the bundling, but it lets me run a local server, which I'll use to test my JavaScript code against a headless CMS. To be clear, I'm focusing in on the JavaScript library part of a Cycler project, and I'm suggesting that this subsection should itself adhere to Helix. My Yeoman add_TypeScript subgenerator adds a base TypeScript library to my Cycler project. I will not show the running of that generator to save time, but I just want everyone to be aware that all the code I will show from here on will be inside the TypeScript library, which lives inside my Cycler project. At its core, Webpack is a module bundler. We tell it what the entry point is, and it uses this to build out its internal dependency graph. Webpack is a node module, so it's installed with npm or yarn with these two commands. The base configuration required is to create a webpack.config.js file at the root of your project, which needs to provide the entry point file, the output file name, which is what Webpack will use to generate the bundle. And Webpack also lets us specify loaders for various file types so that files can be compiled differently. For example, the project I will demo shortly is built in TypeScript. For anyone not familiar with TypeScript, it's basically special syntax on top of JavaScript that allows compile time validation, and it needs to be transpiled into plain JavaScript during the bundling process. So we will tell Webpack to use a TypeScript loader for TypeScript files. We also need to expose a script entry point in package.json, which we will use to trigger the Webpack runs. The script I'm exposing here is named build, so I will be able to run it with the command npm run build. As you can see, this command will do two things. First, it will call yarn to ensure that all the node dependencies required by my project are up to date. And second, it will call Webpack to do the bundling. When devs switch their local environments to a new branch, all they have to do is run this build command, and any dependencies that may have been changed by other devs will be automatically resolved and updated. With the Webpack as our dependency manager and bundler, we can bring Helix and its core principle of modularity to a Sitecore project's JavaScript layer. Let's take a look at an example of how this can be implemented. At the foundation layer, I've placed base infrastructure classes. For example, I have a component factory that initializes UI component classes based on what HTML has been rendered by the server, an event system class that manages interaction between components, and a global context class that houses shared services. At the feature layer, I've placed classes that represent UI components. These classes map directly to Sitecore renderings. They can be grouped together by page type to improve organization. We'll come back to the project level in a minute. This is the TypeScript library that lives inside my Sitecore solution. I've opened a new Visual Studio Code window to scope in just on the TypeScript library root. Let me show you around this project. This project has a source folder for the TypeScript Helix. Here's the foundation folder for base infrastructure classes. And here's the feature folder for UI component classes. Looking at a sample UI component, it uses import statements to pull in dependencies from other files in the tree. My Webpack config has the TypeScript loader that I mentioned earlier. An entry point declaration, which is a file that exports all my classes like this. And it has an output declaration, which tells Webpack where to generate the bundle. I'm going to run this build command to kick off Webpack's dependency resolution and bundling. This will generate a single file in the project bin, which contains my entire TypeScript library. So keep an eye on the top left there, on that bin that just got generated. And now we have main.js, which is the transpiled JavaScript. So Webpack allowed me to bring Helix-style organization to my Sitecore project's JavaScript layer, which is pretty cool. But we can do even more to improve the development process. We can increase speed of development and debugging by enabling on-the-fly compilation. For this, we need a way to serve our library in the browser without going through Sitecore. And we can do this with the node module Webpack Dev Server. To explain how that works, I need to return to this slide and fill in the project layer. This is the layer that's most closely coupled to a specific website. So if we're building a TypeScript project that houses generic components, but needs to provide website-specific context for these components when running in a headless CMS, then naturally the project layer is where such assets should go. So in my TypeScript Helix implementation, the project layer holds static files that mock server responses. This includes HTML files that represent rendered Sitecore pages and JSON files that represent AJAX responses. By mocking website-specific context with static files, we are able to isolate development and testing of the TypeScript library. Webpack Dev Server enriches the bundling and dependency management of Webpack by providing a local host server that watches your files for changes and automatically reloads when changes are detected. To get it running, we need to install this node module, and the webpack.config file needs to be appended with a dev server property. We need to expose another script entry point in the package.json file, which we will use to launch our server. The script I'm exposing here is named dev, so I'll be able to run it with the command npm run dev. As you can see, this command does two things. First, it calls a setup script, and then it triggers Webpack Dev Server. Let me explain the setup script. In the previous demo, we saw how the build command generated compiled JavaScript files in the project bin. The bin is where the local server will be served from. So if all we have in the bin are scripts, that's not enough to render our site. We need one more step to copy the static files from the project layer into the bin. That's what the setup step is for. After the setup, the second thing that the dev command does is launch a server on localhost 9000 using the contents of bin. Let's see this in action. So here's my dev server property in the web config in my project. I can confirm that there's nothing launching on localhost 9000 right now, since I haven't run the command yet. So I'm going to open up a new terminal and run npm run dev. We can see that our static files from the project layer have been copied into bin. And now if I refresh localhost 9000, we have a site. So now here's the cool part. If I go into source and actually open up one of my components, I'm just going to add some simple code in the constructor here, just an alert. And then when I hit Control S to save this, if you'll notice, it automatically recompiled and the browser automatically reloaded with the updated code. Here, we can try it again. So this is what I mean by on-the-fly compilation. I want to dive a little bit deeper into how my headless CMS works. From looking at this colorful page, it's clear that we've successfully mocked the HTML and CSS that Sitecore would serve us on a page load. That's the easy part. It was just a matter of copying static files into the project bin. The other element to my headless CMS is mocking server responses to AJAX calls. Without this, we wouldn't be able to fully test our components in this environment. For example, my sample component here has a call to action button. And when this button is clicked, it's supposed to make a call to the server for data that's used to render additional components. Will this AJAX call work when it's not coming from a Sitecore site context? I actually don't even have Sitecore running during this demo. So will the call fail? Let's see. So if we inspect the network tab, we can see that the AJAX call went out to a JSON file, and it was a GET request. And we did get real JSON back, and that's how these new components were rendered. So the AJAX call worked fine. So there are a few architectural best practices to keep in mind when building components that can function in both a normal and a headless site context. For server interaction, encapsulate all AJAX functionality in an injectable helper, and never hardcode server endpoints. And for UI component classes, accept server interaction helpers as parameters and constructors, and don't talk to the server directly. The key is that anything that depends on the CMS should be injected into TypeScript components via the constructor. It's dependency injection for your JavaScript layer, just like you do in backend code. Here's what this looks like in my implementation. This is the static HTML file that's used to mock the Sitecore layout in a headless context. As you can see, I initialize a class called Global Context, which gets a reference to the Sitecore service. This is my AJAX helper. And I tell Sitecore service to use a JSON file as the place to fetch data from. And when I initialize the same code from a Sitecore context, I simply pass in the real server endpoint to the AJAX helper. Here, I define an MVC route in app start, which can be used to access controller actions. And in my Razor view for layout, I use URL helper's route URL method to generate a fully qualified URL to pass into the AJAX helper. When new instances of UI component classes are instantiated, I inject the global context instance via a parameter in the constructor. This is how all my components get access to the Sitecore service AJAX helper, which is what was used during the demo when the call to action button was clicked. Now we are ready to move on to discussing the testing stage of a Sitecore project. The design patterns that we just went over, which enabled us to inject dependencies into TypeScript components, are the same patterns that make unit testing a breeze. Because everything that was done to mock a Sitecore context for the local server can be reused to mock a Sitecore context for unit testing. Let's see how Jasmine, which is a unit testing framework, and Karma, which is a test runner, supplement our Sitecore project. Real quick, why am I even spending the time on the topic of unit testing JavaScript? Have you ever experienced a scenario like this in Sitecore? You have a page with complex US and a bunch of renderings, and all of them have parallel JavaScript components that are triggering different events and modifying the DOM, maybe a site search page or a shopping cart. Everything works fine, and then one day things break because the content author moved something around or removed a rendering that they didn't know was related. I've seen this happen when the developers assume that content authors will always adhere to designs. So the code functionality depends on a specific set of renderings existing in the page. The issue is that devs sometimes design renderings in terms of pages rather than in terms of components. So I support the design principle that components should be 100% autonomous, and more importantly, they should not directly cause side effects in other components, because content authors should be free to add or remove whatever renderings they want. Server-side unit testing can be used to enforce this design principle across a development team. The purpose of this story is to highlight the value of unit testing the JavaScript layer. Unit tests define the contract for how code is expected to behave. Since the JavaScript layer controls all the front-end behavior and user interaction of your renderings, if you're not unit testing JavaScript, then you're leaving a wide open door for inconsistent development patterns and bugs. To add Jasmine to a project, the Jasmine and Jasmine Core node modules need to be added with NPM or Yarn. If using TypeScript, the Jasmine types module should also be added to inform the TypeScript compiler about Jasmine functions. After that, you can jump right into writing tests. From the Jasmine documentation, this is the example of a most basic test function. Jasmine's describe function is used to wrap a suite or group of tests. Calls to describe can be nested if you want to have several levels of grouping. Inside the callback to describe, Jasmine's it function is used to define a specific test. Here's an example of a Jasmine spec file from my TypeScript project. It will provide more clarity on the usage. On the left, I have one of the shared utilities from the foundation layer. It's a utility for string manipulation called string_util. It exposes two public static functions. On the right is the spec file that tests this class. The first line of the spec file imports the class that I am testing. Then I use describe to define a suite of tests for string_util. Then I have a nested describe, which defines suites of tests for each function in string_util. Finally, I use it to define a set of tests for each function that covers both successful cases and cases that result in errors. As you can see, testing a utility class with static functions is pretty straightforward. Now, how can I test a UI component class? This is the best practices chart for JavaScript components that I shared earlier, but I'm adding one bullet to clarify that when dependencies are injected into UI component classes, this should happen via interfaces, not concrete classes, since interfaces can be mocked during unit testing. Here's what I mean by that. Looking at that sample component from the demo, you can see that the dependency injection of the global context class is done through an interface. Remember, global context is the thing that houses my Sitecore service Ajax helper. When initializing this class in a unit test, I can pass in a mock implementation of global context that stubs out the functions that perform Ajax calls, just like you would do in C# tests. The last rule that I'll add to this best practices chart is in regard to how dependency on DOM should be managed. Your UI component classes should accept a DOM element in the constructor and scope all actions to this DOM element. The sample component accepts an HTML element in the constructor, and all the actions that this component performs, all the DOM manipulations that happened on the button click, are exclusively scoped to that element. With proper dependency injection in place, I can test all aspects of the component. For example, in this test, I provide a mock implementation of the AJAX helper that loads data from a JSON file, and I provide a block of HTML. This represents HTML that will be rendered by Sitecore. The test validates that the component initializes correctly. I can follow this pattern to quickly test a multitude of cases. I can validate that this component doesn't break when it exists in the page multiple times. I can add or remove other components that this component may interact with and see what happens. I can change the content of the HTML to represent changes in content authorizable fields. The nature of these tests reduces the number of test cases that have to be performed manually by QA, which saves significant time. Jasmine is just a unit test framework. A test runner like Karma is needed to run the tests. To get started, install the Karma node module with NPM or Yarn. Then there are a few plugins that need to be installed, and these vary depending on the specifics of your project. In my case, I installed Karma Jasmine since I'm using Jasmine, Karma Chrome Launcher because Karma needs a browser to run, and I selected the one that supports ES6 syntax, Karma Coverage Istanbul Reporter and Karma Spec Reporter show code coverage percentages, and Karma Webpack generates Webpack bundles during test runs. Similar to other node modules that we've seen today, the package.json file needs to be adjusted to export another entry point for Karma. The script I'm exposing here is named test, so I'll be able to run it with the command npm run test. From there, there's just a bunch of configuration that needs to be adjusted. All the available options are documented on Karma's site. The main ones to note are the frameworks property, which specifies that I'm testing with Jasmine, the files property, which specifies which files to load, the preprocessors property, which configures which files should be tested for coverage, and the reporters property, which activates code coverage. The Webpack property gets a reference to the project's Webpack configuration. But during Karma runs, I have to extend the base Webpack configuration with an extra loader to make it work correctly with the Istanbul code coverage tool. I'll admit that it can be a bit painful to get the configuration just right for Karma, but that's just a one-time setup. Let's take a look at a demo of running the tests. So I'm going to open up a new terminal window and run npm run test. So this is what a Karma output looks like. We can see our code coverage summary here on the bottom. And then if I scroll up, we see details from all the unit tests that were run. Karma also adds a bunch of reports to our bin, and these can be used if you're running the tests from CI/CD. Here's an example of one of the reports. So that's it for my presentation. The code that you saw from our Yeoman generator can be downloaded from this repository. And if you have any questions for me, you can hit me up on Twitter.